A very good evening, students. So, in last class, we discussed various loss functions, and today we shall discuss the last parameter associated with neural networks, which is optimizer. So, let us discuss optimizers. Okay, let me first let you know that what exactly the optimizer is. So, in mathematical terminology, we say that optimization algorithm is the task of minimizing or maximizing an objective function that is parameterized by some variable, say x. So, similarly, in machine learning, also, optimization is the task of minimizing the cost function that is parameterized by the model's parameter. Okay, so here also, like this function is parameterized by some parameters and they are model's parameters. So, the meaning is same here. Optimization is very important component for training process because it involves finding the optimal set of parameters for the model that can minimize the loss, or you can say cost function or error on the training data. So it is very important. And optimizers are algorithms which are used to find the optimal set of parameters for a model during the training process. And this optimization algorithms, they adjust the weights and biases in model iteratively until they converge on a minimum loss value. So here also, like we are using this optimization function for almost the same purpose as we use this optimization functions or algorithms in other real time domains, like meaning is the same. Fine. So here you can see the list of optimizers available for machine learning models. So I may discuss some of them in detail, and then I may introduce rest of them briefly. For example, gradient descent and types of gradient descent, I will discuss in detail because this is very popular optimization algorithm used for machine learning models and neural networks. And the rest also I will discuss, but not in detail. I'll simply introduce them, and later you can go through them in detail once I introduce them. Fine. Because today I wish to complete this unit so that we can focus on convolutional neural network. Okay, fine. So let us start with this gradient descent optimization function. Gradient descent, gradient descent is known as one of the most commonly optimization algorithm to train all machine learning models by means of minimizing errors between actual and expected results. Gradient descent is also used in neural network along with other machine learning models. So mainly like here we are discussing neural networks. So I'm letting you know that this is used for neural networks too. So this gradient descent, it was initially discovered by Augustine Lois in mid of 18th century. So this is not discovered today or in recent years. After, like we know that in last one decade, this machine learning and deep learning techniques, they have been very popular. But not after, like in last one decade, though those techniques have been popular, this gradient descent is not discovered in last one decade or in last some decades. It is there since 18th century. This gradient descent is defined as one of the most commonly iterative optimization algorithm of machine learning to train the machine learning and deep learning models. And it helps us in finding the local minimum of a function. Last time I told you that I'll let you know what exactly the local minimum is. I'll also show you the slide which will give you clear idea about the local minimum and global minimum, but I have included it after the discussion of gradient descent. Here we will discuss only local minimum. Okay, so this is like, as I have told you, this is to find the local minimum of a function. Fine. Now, the entire procedure of this gradient descent is known as gradient ascent, which is also known as steepest descent. And the main objective of using gradient descent algorithm is to minimize the cost function using iteration, right? To achieve this goal, that is to minimize the cost function using iteration, this optimizer performs two steps iteratively. The steps are performed iteratively, and these are those two steps as mentioned here. The first step is calculate the first order derivative of the function. Calculate the first order derivative of the function to compute the gradient or slope of that function. And the second step is move away from the direction of the gradient. Move away from the direction of the gradient, which means slope increased from the current point by alpha times, where alpha is defined as learning rate. Because if you remember, I told you in last class also, this optimization functions are useful to get the optimal values for weights and learning rate. So here alpha is defined as learning rate, and it is like we know that it is one of the tuning parameters for our machine learning models. Okay. So that is about the brief about the gradient descent, that how it is performed. Okay. I'll show you in this figure later. Let us first discuss uh, the how this which are the main steps performed by gradient descent to achieve this goal. So the main objective of using this gradient descent algorithm is to minimize the cost function using iteration, as we just discussed. Okay, so here are the steps performed to achieve that goal. And okay, this steps you, I think, yeah. Yeah, I just discussed the steps earlier. I was in this slide where it is written. Now, okay, as you can see here, I forgot to discuss this point, that if we what does exactly it means? The best way to define the local minima is as given in this figure. If we move towards a negative gradient or away from the gradient of the function at the current point, it will give you local minimum. So you look at this figure, there is a red circle in this figure, and that is the current it is the gradient of the function at the current point. Now if you move away towards the negative gradient, we are moving down. You can see the arrows here, we are moving down. So if you move away, or you if you move towards a negative gradient, it gives you local minima. So here at the bottom of this blue curve, you will have local minima. Okay. And what is local maximum? Whenever we move towards a positive gradient or towards the gradient of the function at the current point, we will get the local maximum of that function. So this is about the local minima and local maxima. And here are the steps which are used to find the local minima in gradient descent. Now, this is about the simple gradient descent, and it works for most of the machine learning models. But we also have variations of this gradient descent. And here are the variations of gradient descent. We have three types of gradient descent: batch gradient descent, stochastic gradient descent, and mini batch gradient descent. So let's see that how they differ from each other, and how they what is difference between a simple gradient descent and this variations. Okay, so this types based on the error in variation, based on the error in various training models, the gradient descent learning algorithm is divided in these three categories, that is batch gradient, stochastic gradient, and mini batch gradient descent. Okay, now what is batch gradient descent? So here is the batch gradient descent. Batch gradient descent is used to find the error for each point in the training set and update the model after evaluating all training examples. I repeat, this is used to find the error for each data point in the training set and update the model after evaluating all training examples. Whatever number of data points are there, in the data set, for them error is calculated and then update the model after evaluating all this training examples in data set. This procedure is known as the training epoch. That is, one epoch gets completed when you compute error or when you train your model for all the samples in your training data set. In simple words, we may say that it is a greedy approach where we have to sum over all the examples for each update, because we are computing error for every data point in training data set, and then we sum over all examples for each update. So this is like entire batch is considered to compute the gradient. And this is a batch gradient descent. What are the advantages of this batch gradient descent? Here are the advantages. Like, it produces less noise in comparison to other gradient descent, which we will be discussing now. It produces stable gradient descent convergence, and it is computationally efficient as all resources are used for all training samples. Okay, these are like some general benefits of batch gradient descent. Now let's discuss the stochastic gradient descent. Like, procedure is different for computing the gradient descent in each of this type. Now, what is stochastic gradient descent? Stochastic gradient descent is a type of gradient descent that runs one training example per iteration. Please understand, the previous one was batch gradient descent. This is stochastic gradient descent. In batch gradient descent, we compute error for all the examples in training set, right? So during one iteration, during one epoch, the error for all training examples is computed, and that is then like we sum all of them. Now here, this stochastic gradient descent runs one training example per iteration, or we can say that it processes a training epoch for each example, one training epoch for each example within a data set, and then it updates each training example's parameters one at a time. So this is how it differs from batch gradient descent. As stochastic gradient descent requires only one training example at a time, it is easier to store it in allocated memory. That is the advantage of stochastic gradient descent, that it is easy to store it in allocated memory because only one training example at a time. However, it shows some computational efficiency losses in comparison to batch gradient. Computational efficiency loss in comparison to batch gradient system because it shows frequent updates that require more detail and speed, because at a time it is processing only one example per one sample per iteration. Moreover, due to frequent updates, it is also treated as the noisy gradient. While previous, like batch gradient descent doesn't produce noise, but stochastic gradient descent, it is treated as a noisy gradient. However, sometimes this stochastic gradient descent can be helpful in finding the global minimum and also escaping the local minimum. That is the advantage. So here are the other advantages of stochastic gradient descent. Learning happens on every example in stochastic descent, and it consists of advantages like it is easier to allocate in desired memory. It is relatively fast to compute than batch gradient descent because only one sample at a time, while in batch gradient descent, entire batch is considered to compute the gradient. This is more efficient for large data sets, stochastic gradient. So there are some of the advantages. Now, the next is mini batch gradient descent. So how it differs from the previous one? How it differs from batch gradient descent and stochastic gradient descent? Mini batch gradient descent is the combination of both batch gradient descent and stochastic gradient descent. It it's as it is a combination. I repeat, In batch gradient descent, entire batch is considered, entire training data set is considered. In stochastic, one sample from training data set at a time in one iteration. Okay. Now in mini batch gradient descent, what as it is a combination of these two, we consider batch, but we do not consider the full batch. We consider the mini batch. We consider the mini batch. So what is mini batch? It divides the training data set into small chunks. They are called mini batches. It divides the entire DNA. For example, there are say, this is just an example. Let's say there are 1000 samples in your training data set. So it may divide your batch, it may divide your full batch into mini batches of size 100. So you will have 10 mini batches, 100, because total 1000 samples are there, which are divided into 10 mini batches of size 100. So this mini batch divides the training data set into small batch sizes, and then it performs the updates on those batches separately. So splitting training data set into smaller batches, smaller chunks, make a balance to maintain the computational efficiency of batch gradient descent and speed of stochastic gradient descent. So this is very popular among all this three mini batch, because it provides benefits of both gradient descent, like batch gradient descent and stochastic gradient descent both. So we can achieve a special type of gradient descent with higher computational efficiency and less noisy gradient descent. So here are the advantages. As you can see, it is easier to fit in allocated memory, which is advantage of stochastic gradient descent. It is computationally efficient. Okay, it is also advantage of stochastic gradient descent, which is known as SGC. Okay, and it produces stable gradient descent convergence. So, like this is very popular among all three. So, this is about the gradient descent and variations of gradient descent. Though it is widely known and popular, this optimization algorithm, it has some challenges too with it. So here are the two main challenges associated with gradient descent: local minima and saddle point, and the second is vanishing and exploding gradient. So let me tell you briefly that what they are. Okay, this local minima and saddle point. Let us talk about the local minima and saddle point first. For convex problems, gradient descent can find the global minimum easily. Convex problem, okay? So, of course, it is very easy to find the global minimum. While for non-convex problems, it is sometimes difficult to find the global minimum, where the machine learning models achieve the best results, global minimum. Okay, I think I added that slide at the end, but I think I should show you first global and local minima. Okay, then I'll talk about the global minima. So this figure shows you what is local minima and what is global minima, and what is local maximum and what is global maximum. So here you can see that on left side figure, like there is one, this is one convex, one curve. Okay, so each convex can have one local minima. So there are several local minimas here. You can see that three local minimas are there in left hand side figure, that on red curve you can find three local minimas. Among these three local minimas, the local minima, the rightmost local minima is the global minima, because it is lowest among these three local minima. It is lowest among these three local minima. So it is called global minima. Okay. And similarly for global and local maximum also, we may have several local maximum, but only one can be global maximum. So in left hand side figure, there are two local maximum, And like one of them is has higher value. The one which is having the higher value is considered as the global maximum. Even in right side figure, you can see the same thing, like local maximum and global maximum. Among the several local maximums, the one which is having the maximum value is considered global maximum. So I hope this is clear now. What is okay now? What you can see that in right hand side figure, the global minimum minus infinity, right? It can be considered as global minimum, and similarly, positive infinity can be considered as like a default global maximum. Okay. Now, let me tell you about this local maxima and saddle point. Okay. Yeah, we were discussing about fine local maxima. Huh. Huh. So here you can see that for convex problems, gradient descent can find the global minimum easily. While for non-convex problems, it is sometimes difficult to find the global minimum where the machine learning models achieve the best result. Global minimum is the point where machine learning models achieve the best results. Okay. So whenever the slope of the cost function is, whenever the slope of the cost function is at zero or just close to zero, the model stops learning further. Okay, whenever the slope of the cost function, of course, because when it is nearer zero, that means there is no error. And no error, then model should stop learning because it has converged. So whenever the slope of the cost function is at zero or just close to zero, the model stops learning further. Apart from the global minimum, there occur some scenarios that can show this slope, which is called saddle point and local minimum. Local minima generate this shape similar to the global minimum, where the slope of the cost function increases on both sides of the current points. Okay, so saddle point is shown in the figure on the right hand side. You can see that like yellow color point is the saddle point. Okay, and in contrast with saddle points, the negative gradient only occurs on one side of the point, which reaches a local maximum on one side and a local minimum on the other side. Local maximum on one side and local minimum on the other side. And the name of saddle point is taken by that of the horse saddle. Okay, so you can see that on the line, one red point on the right side, one red point on the left side. In between, there is a saddle point. Okay. So name of local minima is because the value of the loss function is minimum at that point in a local region. Okay. Why it is called local minima? Because value of the loss function is minimum at that point in local region. That's why local minima. And in contrast, the name of global minima is given because the value of the loss function is minimum there globally across the entire domain. Entire domain, the loss function is minimum. That is global minima. Okay, so this is about the local minima and saddle point. The second is vanishing and exploiting gradient. In deep neural network, specifically in deep neural network, if the model is trained with gradient descent and back propagation, there can occur two more issues other than local minima and saddle point. I thought to discuss this problem with the last topic of this unit, which is back propagation and gradient descent. But I'm discussing here because we are discussing gradient descent. Because that is the point, that is the topic about back propagation. So this vanishing and exploding gradient problem occurs if the model is trained with gradient descent and back propagation. And this is specifically occur in deep neural network. There can occur two more, like these are the two more issues specifically for deep learning when gradient descent and back propagation are used. Vanishing gradient vanishing gradient occurs when gradient is smaller than expected. When gradient is smaller than expected, and that's why its name is vanishing gradient. It is smaller than expected. During back propagation, this gradient becomes smaller than it becomes smaller. During back propagation, this gradient becomes smaller. That causes the decrease in the learning rate of earlier layers than the later layer of the network. And once this happens, the weight parameters update until they become insignificant. So gradient becomes smaller than the expected. And when it becomes smaller than the expected, it causes the decrease in the learning rate of the earlier layers than the later layers. So this is called vanishing gradient problem. The learning rate of the earlier layers become smaller than the learning rate of the later layers in the network. And what is exploding gradient? Of course, it is just opposite to the vanishing gradient because this is exploding gradient. So exploding gradient is just opposite to vanishing gradient as it occurs when the gradient is too large and creates a stable model. In this scenario, in exploding gradient, model weight increases and they will be represented as not a null value. So this problem can be solved using the dimensionality reduction technique, which helps to minimize complexity within the model. Okay, so this is about the exploding gradient. Fine. Okay, I can see one question in chat box from Hiten. Can we say that a local minima, the training data set of that local area is of minimum cost, but not for all the data set? Yes, you are absolutely right, Hiten, that for local region, it is a minimum, but not like for whole data set. Minimum cost, but not for all the data set. While a global minima, all the data set have minimum. Like it is over entire data set. Global minima is over entire region. Yes, you are right. Okay. So this is about the problems associated with this gradient descent. Fine. Local minima and global minima we discussed. So far we discussed the gradient descent and its subtypes. So 4 optimizers we discussed: gradient descent, batch gradient descent, stochastic gradient descent, and mini-match gradient descent. Now there are also other like stochastic gradient descent with gradient clipping, momentum, Nestero momentum, EDA grade, EDA delta, RMS prop, Adam, then EDA max, and squared mean over root mean squared cube. These are other optimizers available in literature. So let me give you a brief idea about the rest of the optimizers, and I suggest you go through these optimizers later in detail if you otherwise also like I am sure that through a lecture you cannot, through this one class you cannot remember about the topics discussed in this 1 hour session. You must go through all these topics during your free times to make the concepts more clear to you, because you cannot learn anything in one go. Repeated learning like like artificial neural network or biological neural network also needs repeated learning, right? To memorize the things, then only you can remember. Okay. So it's like same law, same principle to remember things accurately. Okay. So let me tell you briefly about the rest of this. Okay. Stochastic gradient with descent, stochastic gradient descent with gradient clipping. So I'll just tell you that how it differs from stochastic gradient descent. Stochastic gradient descent with gradient clipping is a variant of this standard SGD. Stochastic gradient descent is also known as SGD. Okay, so this is a variation of standard SGD that includes an additional step to prevent the gradients from becoming too large during training. Just we discussed that problem of exploding gradient. So this is to overcome, this is to avoid that problem. So this SGD with gradient clipping includes an additional step to prevent the gradients from becoming too large during training, which can cause instability, because when it becomes too large, it causes instability and slow convergence. So to overcome these disadvantages, it adds an additional step. So that additional step prevents gradients from becoming too large. Okay. So scaling, actually gradient clipping involves scaling down the gradients if their norm, if their value exceeds a predefined threshold. Okay, so threshold is defined in this method, and gradient clipping, like scale, it scales down that gradient if it reaches beyond that threshold. So this helps to prevent the exploding gradient problem, which can occur when the gradients become too large and causes the weights to update too much in a single step. Because if gradient is too large, there would be a too much update in weight. So in one single step. So to avoid that, this is required. Okay. So this is stochastic gradient descent with gradient clipping. You can go through it in detail, like referring to more literature. Okay, the next is momentum. I'll give you crisp idea behind all this optimization algorithm so that you can remember. Okay. Momentum. Momentum is an optimization technique. Uh, it is used to, like as other optimization algorithm, it is also used to accelerate the training of neural networks. It is based on the idea of adding a fraction of the previous update. It is based on the idea of adding a fraction of the previous update to the current update of the weights during the optimization process. In this momentum optimization, the gradient of the cost function is computed with respect to each weight in the neural network. And instead of updating the weights directly based on the gradient, momentum optimization introduces a new variable, which is called a momentum term. It is called a momentum term, which is used to update the weights. So it does not consider only gradient, but along with gradient, a variable called momentum term is used to update the weights, and the momentum term is a moving average of the gradients. Please listen carefully. It is what is momentum term, which is used to update the weight. Momentum term is a moving average of the gradients, and it accumulates the past gradients to help guide the search direction. So this is like momentum. This is called momentum optimization algorithm. This is how it works. Uh, okay, if I tell you a bit more about this, a momentum term can be interpreted as the velocity of the optimizer, because optimizer accumulates momentum as it moves downhill and helps to like dampen oscillates in the optimization process, and this can help the optimizer to converge faster and to reach a better local minimum. Okay, so that is okay, momentum. uh, okay, the next is Nestero momentum. Nestero momentum is a variant of the momentum optimization technique. It is named after the mathematician Yuri Nestero. So this is the surname of inventor of this optimization technique. He proposed this idea. In standard momentum optimization, as we just discussed, the gradient of the cost function is computed with respect to each weight in the neural network, and the weights are updated based on the gradient and momentum term. While Nesterov momentum optimization modifies this weights by first updating the weights with a fraction of the previous momentum term and then computing the gradient of the cost function. So this is all, like all these optimization functions are mathematical functions, So they slightly differ from each other, right? So mathematicians and computer science researchers, based on their understanding, they tried various different terms, like they added or they removed, or that way, mathematical terms were added, and different optimization functions were invented. So idea behind this nested row momentum is that the momentum term can help to predict the next location of the weights, which can then be used to compute a more accurate gradient. So this can help. Once they think of the idea, they propose the new equation, new cost, the new optimization function. They experiment with the existing optimization functions, and if they find improvement over the existing optimization function, then like a new optimization technique is invented. So this is how like you can also try with the new optimization techniques and experiment with different available optimization techniques and check, right, that how they are performing. Okay, so this nested row momentum can help the optimizer to take larger steps in the right direction, and this is how they help neural network to converge faster than standard momentum optimization. Okay, the next one is ADA grade. It is known as adaptive gradient. ADA stands for adaptive and grade stands for gradient. Adaptive gradient. This is an optimization algorithm used to optimize the training. This is also like along with other machine learning models, this is used to optimize the training of neural networks too. ADA grade algorithm adjusts learning rate of each parameter of the neural network adaptively. It adjusts learning rate of each parameter of the neural network adaptively during the training process. Specifically, if I tell you, it scales the learning rate of each parameter based on the historical gradients computed for that parameter. Based on the historical gradient computed for that parameter. In other words, I can say parameters that have large gradients are given a smaller learning rate, while those with small gradients are given a larger learning rate. I repeat, parameters that have larger gradients that have large gradients are given a smaller learning rate, while those with small gradients are given a larger learning rate. And this technique helps it helps to prevent the learning rate from decreasing too quickly for frequently occurring parameters and allow for faster convergence of the training process. So this ADA grade algorithm is particularly useful for dealing with sparse data, where some of the input features have low frequency or they are missing in your data, because data is sparse data and some of the input features may be missing, or they may have low frequency, right? So in this cases, ADA grade is able to adaptively adjust the learning rate of each parameter, which allows the better handling of sparse data. So overall, ADA grade is a powerful optimization algorithm that can help accelerate the training of deep neural networks and improve their performance. Okay, the next is ADA delta. ADA delta is an optimization algorithm used to optimize the training of neural networks also, and it is variant of ADA grade algorithm. ADA delta is variation of ADA grade algorithm and addresses some of the limitations of ADA grade algorithm. So it's a variation of ADA grade. Okay, the ADA delta algorithm adapts the learning rate of each parameter in a similar way to ADA grade, right? It is a similar way, but instead of storing all the past gradients, which we use in ADA grade, instead of storing all the past gradients, it only stores a moving average of the squared gradient. It only stores a moving average of the squared gradients. This helps to reduce the memory requirements of the algorithm. That is the biggest advantage of ADA delta, that it reduces the memory requirements, because we are not storing all the past gradients. We are simply storing one value, average of the squared gradients. Additionally, ADA Delta uses a technique called delta updates to adjust the learning rate. So instead of using a fixed learning rate, ADA Delta uses the ratio of the root mean squared of the past gradient and the RMS of the past updates to scale the learning rate. And this may help to further prevent the learning rate from decreasing too quickly for frequently occurring parameters. So this is how ADA delta differs from ADA grade. Okay. Next is RMS drop, root mean squared propagation. RMS stands for root mean square. Prop stands for propagation. So this RMS prop is an is like ADA grade and ADA delta. It also adapts the learning rate of each parameter during the training process, similar to ADA grade and ADA delta. However, see how it differs, okay, from both of them. Instead of accumulating all the past gradients like ADA grade, RMS drop RMS prop computes a moving average of the squared gradient like ADA delta. This allows the algorithm to adjust the learning rate more smoothly and prevent the learning rate from decreasing too quickly. RMS prop also uses a decay factor. Right, there we were in ADA delta, we were using delta factor. Here we are using decay factor to control the influence of past gradients on the learning rate. So this is how it differs from ADA delta. So ADA delta and RMS prop, they work similar to ADA grade. Only difference between ADA grade and ADA delta RMS prop is instead of accumulating all the past gradients, they store a moving average of the squared gradient in both ADA delta and RMS prop. And difference between ADA delta and RMS prop is ADA delta uses delta while RMS prop uses a decay factor to control the influence of past gradients. This decay factor allows this optimization techniques to give more weight to recent gradients and less weight to older gradient. Please understand this. What is the importance of using, what is the benefit of using this decay factor? Decay factor is used to give more importance to recent gradients and less importance to older gradients. So this is how it differs from the previous two optimization techniques. And one of the main advantage of this RMS prop over ADA grade is that it can handle non-stationary objectives. Sorry. Yeah, so this is about the RMS prop. Next is ADAM. ADAM is also very popular. Adaptive moment estimation. Adaptive. ADA stands for adaptive. M stands for moment estimation. So ADAM is ADAM combines the concepts of both momentum and RMS drop. So now if you remember this both like momentum and RMS drop, then you can based on the variance of the gradients. Okay, so this is how ADAM works. ADAM Max is a variant of ADAM optimization algorithm. Like ADAM Max also maintains the moving average of the gradient first and second moments. However, instead of using the second moment of the gradient as in ADAMX, instead of using the second moment of the gradient as in ADAMX uses the L infinity norm of the gradient. And this is useful in situation where gradients are very sparse or have a very high variance. So that's why like maximum L infinity norm of the gradient is used. And the use of L infinity norm in ADA makes it more stable than Adam when dealing with sparse gradients. Okay, and the last is squared mean over root mean squared cube. Uh, this is this modifies the way the moving average of the square gradient is calculated in RMS prop. Instead of taking the simple average of the squared gradient, this squared mean over root mean squared cube takes the cube root of the moving average of the cube. Cube root of the moving average of the cube of the squared gradients. So this is how it differs from that RMS prop. So otherwise, it is functioning similar to that of RMS prop, right? So these are all optimization techniques. I purposefully did not include the equations of all these optimization techniques because they include many notations. And like I thought, let me first give you brief idea about uh, what is optimizer and which are the popular optimizers like gradient descent and Adam, and others are the variations of the existing optimization techniques only. They differ by one or the other points like from the existing one. And once you understand the classic optimization techniques, it's very easy to understand their variations also, right? So but I suggest that you go through the fundamental optimization techniques first in deep, and then you go through the functions equations of all the rest of the like latest these are not okay, let me tell you the list which I have included in this slide, the list of optimizers. This is not the this are not only the optimizers. You will also find some more in literature. Okay, but these are the popular optimizers. And just I wanted to convey that how they differ from each other. Fine. So mathematical terms like they are mathematical terms in optimization technique. They are changed, and their effect is checked. It is verified experimentally, and then a new optimization technique is proposed if it is found beneficial. So this is how several optimization techniques are available. But as I told you, your biological neural network can remember only if you learn, if you go through multiple epochs. Okay, so do not rely only on one class to understand the optimization technique. Okay, so this needs, as I told you previously, that concepts of machine learning, the fundamental concepts of machine learning should be very clear to you to understand deep learning networks like properly. Fine. Fine. So these are all optimization techniques. Now, okay, pros and cons. I told you during discussion that how this optimization techniques differ from each other during the discussion. However, you can go through pros and cons when I provide you the slides. Okay. So in this table, I have included the pros and cons of different optimization techniques, which help you to decide that which optimization technique or techniques you should try for your machine learning problem or deep learning problem. Okay. So it is like never that you, when you work on any machine learning, deep learning problem, you can never decide that this will be the best optimization technique for my problem. No, it's not like that. You, based on your problem domain and problem and other things like data set and all, you should choose a subset of optimization techniques, maybe like say mini batch, Adam, you have chosen like based on your problem domain and based on your data set and other parameters, you have chosen some of the optimization techniques. Then experiment them, experiment each of them, and then check that which among them is giving you the good results. And then that can be used for your network. Okay. So it is like in one go, you can never determine that which is the best optimization technique for your problem. Fine. So these are, they were the pros and cons. Now, the two topics which are left in your first module are feed-forward network and back propagation with gradient descent. So let us discuss feed-forward neural network. This feed-forward neural network, as you can see in this diagram, okay, the process of receiving an input to produce some kind of output to make some kind of prediction is known as feed forward. You are feeding data in forward direction. You are feeding data in forward direction. So that is called feed forward. Okay. In feed forward neural network, okay, this feed-forward neural network is the core of many other important neural networks, such as convolutional neural network, which we are going to discuss in this subject. Okay, in this feed-forward neural network, there are not any feedback loops or connection in the network. There is no back propagation. There are no feedback loops or connection in the network. And in this figure, you can see that it is simply an input layer, hidden layer, and output layer. Like hidden layers are there, input and output layer. There can be multiple hidden layers which depend on the kind of data you are dealing with. And the number of hidden layers is known as the depth of the neural network. I don't know whether, like you must be knowing, earlier we might have discussed that number of hidden layer is known as the depth of the neural network. The deep neural network can learn from more functions. Input layer first provides the neural network with data, and the output layer then make predictions on the data, which is based on a series of functions. ReLU function is the most commonly used activation function in the deep neural network. So let me tell you the major steps in such feed-forward neural network. To gain better understanding, I tell you the steps. The first step is the input is fed to your neural network, which is presented as uh, like you may say multi-dimensional array. It may be single dimensional array or multi-dimensional array. It is fed to input is fed to input layer, and bias is also taken. Each input is multiplied by weight, as you all know, with respect to the first and second. Okay, each input in first layer, that is input layer, is multiplied by weight, and then what we do that we obtain their probability of being the positive region in each model. After that, we will take the sigmoid of our scores and gives us the probability of the point being the positive region in model. Then we multiply the probability which we can obtain from the previous step with the second set of weights. This is like first hidden layer. We are over with first hidden layer. Now, the probability which we have obtained from the previous step is multiplied with the second set of weights. And we always include a bias of 1 whenever taking a combination of inputs. So this process goes on, right? This process goes on, and finally we get the predicted output. So this is called feed forward, right? Nothing is given back to the neural network, feed forward. Okay. So it's a very simple concept. There may be multiple hidden layers, right? Feed forward. No feedback loops are there. Okay. And why I have used like feed forward neural network were there, and uh, since the inception of this deep neural networks, deep feed forward neural networks are also available. So only difference is we have more number of hidden layers in deep feed forward neural networks. Back propagation and stochastic gradient descent. Back propagation, if we use this is our simple process. What happens in feed forward neural network, like bias is added and how the computation happens. Okay, so one example is included here, that how computation happens in feed forward neural network. Now, what is back propagation? Back propagation propagates the error backward and calculates the gradient for each weight. अब हमने सारा डिस्कशन ये ऑलरेडी कर लिया है. So at last, I'm simply introducing, like, you can consider this as a summary of what we discussed previously. Already we discussed that error is computed, it is propagated. So that is called back propagation. Back propagation, right? So we are propagating this error backward and calculates the gradient for each weight, and this gradient is used in the process of gradient descent. So gradient descent involves adjusting the weights of the neural network, and adjusting the weights help minimize the output error of the neural network. So this is called back propagation and gradient descent. So just the concept is propagation of error back to the network. So, like as we know, gradient descent is used to find a weight combination that minimizes the cost function, and back propagation propagates the error backward and calculates the gradient for each error. So that is back propagation. Yeah. So, this is this two topics I included at last because indirectly these two concepts were covered in our previous discussion. So just I'm telling you in brief that what is feed forward, and here like error is not back propagated. This is back propagation where error is propagated back to the network to adjust the weights. So this is all about the first unit, topics of the first unit, right? Uh, I covered several topics in brief because this unit includes topics of machine learnings like for revision, because you need to revise concepts related to artificial neural network when you want to learn deep neural network. So our subject is deep learning for computer vision, wherein we will learn convolutional neural network, which is very popular for computer vision applications. So, but until and unless you have clear idea about artificial neural network and all the terminology related to artificial neural network, you cannot learn any deep neural network. So first unit is revision of, like you can say, a part of machine learning, because ANN, artificial neural network, is one of the model used to create machine learning, one of the models used to solve machine learning problems. There are other algorithms too, right? So now, if you have any questions, I would like to take your questions. I suggest that please go through all these topics thoroughly to clear, like to make your foundation of this subject strong, so that you can learn the rest of the topics like clearly. If you have any question, you may turn on your mic, or you can write in chat box. No, I could not hit, but anyway, I could not. But I'll do something, and I'll make notes again. But that was too good, and like I was also disappointed when it got corrupted, because that is like wholesome note on all these topics. So I'll provide you PPT and notes of the first